Saxon Advanced Algebra, lesson 85. This is a full lesson, ladies. It's not horribly long and it's not horribly complicated, but it's two topics that kind of tease your brain a little bit in opposite directions. So buckle in and we'll have some fun and hopefully you won't go crazy. What a lead in, right? Okay, what we're going to do in this first section is we're going to take these new trig identities that we've been working with and we're going to use them in equations. Oh, that's kind of interesting. So have your trig equations handy on your, it's not a cheat sheet, it's a data page. Especially these Pythagorean identities, the one with the squares. Keep that one handy. And we'll need unit circles as well. So if you don't have those things at your fingertips, go get. Pause me now. All right, I'm going to dive right in. Solve 3 Okay. When I start to see the squared functions, I immediately think that we're doing just a basic trig identity problem, but we're not. We're solving an equation, but we're going to use those identities, as I already said, spoilers, to solve that. So when I see this secant here and I see tangent, I think, oh, we have a trig identity for that, right? If I can change this tangent squared into secant squared, at least they'll be the same function, and that will be good. So I'm going to use, it's a variation of the equation C. I'm going to use the identity that tangent squared theta equals secant squared theta minus 1. Remember that for the review problem this week, we're going to do memory testing on the trig identities, so make sure you have those. Okay, so that's the one we're going to use. We're going to substitute that in right there, so let's do it. 3 times the quantity, secant squared theta minus 1, quantity, right? We have to put parentheses around that because we'll have to distribute, equals 7 secant of theta minus 5. Okay, let's distribute. And then, just for fun, you'll see why in a minute. We're going to swim both of these over and set the right-hand side equal to 0. So that'll become minus 7 and plus 5. Right? Change sides, change signs. Okay, let's clean that up and look and see what we've got. So I'm going to put them in order. 3 secant squared theta minus 7 secant of theta plus 2 equals 0. Right? The minus 3 and the plus 5. Now, I'm going to now change your world upside down. And we're going to go talk about the advanced factoring that we did end of Algebra 1, I believe. It's quite near the end, and we did it on and off through Algebra 2. But what I'm going to do is I'm going to take the same expression, but I'm going to rewrite it with just x's so that you can see it better. 3x squared minus 7x plus 2 equals 0. Okay, see how I did that? It's the same values and signs. I just rewrote it this way. Do you remember factoring? We called it advanced factoring. What we did was we took this term and we split it into 2 pieces so that we could factor in pairs, okay? So I'm going to show you how we would do that. This one's easy because we don't have many options. I'm sorry, I'm saying that wrong. We multiply together the a and the c, right? If this is ax squared plus bx plus c, we multiply together a and c. In this case, that would be 3 times 2, which is 6. Now we're looking for a number that multiplies to this and adds to that. Okay, so what multiplies to 6? What two factors multiply to 6 but add to that? Well, it would be minus 6 and minus 1, right? They multiply to positive 6 and they add to minus 7. So we're going to rewrite this in here. I'm dropping the 1 out. But I'm taking these two factors and creating two terms in the middle where there was just 1 before. It's equal though, because if I combine those, I still get 7x. And now we're going to factor in groups. Between 3x squared and 6x, I can take out a 3x, and I'm left with x minus 2, right? Now, I want to factor something over here. I want it to end up looking just like this with what's left behind. So I'm going to pull a minus 1 out of this. This makes this minus x a positive x, and the plus 2 a minus 2. Okay, yay. And these are all equal to 0. All right, now I can rewrite this as 3x minus 1 quantity, x minus 2 quantity, and then using the zero product theorem, if two things together multiply to 0, then either the first one is 0 or the second one is 0. So I can say either 3x minus 1 equals 0 or x minus 2 equals 0. And then doing, I'm flying through this, aren't I? Doing a quick little algebra. This is the expression that always comes in my head. I want to hit it with an algebra stick. It will automatically make the 1 go over and then divide it by the 3. So this will give me x equals 1/3 or x equals positive 2. Now, we've been pretending that we're working with x's all this time, right? We simplified it. But what I remember is that what we were really doing was secant the whole time. But we took the secant out because we didn't want to confuse ourselves. So now we're going to put it back in. So what we can say is that the secant of theta equals 1/3, or the secant of theta equals 2. Secant is equal to 1 over cosine, right? They're reciprocal. So that would mean the cosine of theta equals 3, or the cosine of theta equals 1/2, right? I just flipped those and changed the name. Does that make sense? So far, so good, right? Now, here's the problem. These look like good answers that we could take to our unit circle, but this doesn't look right to me, and there's a reason for that. Cosine never goes above 1, right? We know that from our sinusoids. Here, let me show you. I happen to have this handy. Cosine, as a basic function, never goes above 1 or below 1, right? I mean, we can change the amplitude, but the basic function of it never goes above 1 or below minus 1, I should say. I didn't say that right. All right, so we can eliminate this. It's not a solution. There's no way that the cosine can be equal to 3. That means we're left with the cosine of theta being equal to 1/2. We know we want degrees for an answer because that's the way our constraints were placed. So what we're going to do is go to our unit circle and look to see what angles would give me a cosine of 1/2. Here's mine. Cosine is the first number in the pair. So I just look around. Aha, there's one right there. 60 degrees. And there should be one more. Over here, cosine's negative. Over here, cosine's negative. So it must be fourth quadrant. And here's a positive 1/2 at 300 degrees. That makes sense because it's 60 above and 60 below, right? I always like to double check my unit circle numbers and make sure they make sense. So that is the answer for our first problem. 60 degrees and 300 degrees. Whew! Kind of exhausting, but kind of cool, right? Look, I'm really happy about that. Okay, fabulous. Let's try the second one, which is more or less the same. Example 85.2. I'm getting close to the end of this book, you guys, and it's so hard to keep it curled over. You know, I have it folded over like this so that it'll fit here in my viewing stand, but look, it just wants to spring to life. So I have to hold it down like it's a wild animal. All right, solve. 2 sine squared x equals 3 plus. And we have the same constraints placed on it. Oh, except it's x, not theta. So this, again, this tells us right away that, oh, we're looking for degrees as our solution. We're going to need to use our unit circle. And that's our goal, right? That's what this always reminds us. We don't have to do the extra spins. We've got the limiter on there. Praise the Lord. All right. Again, we see the same thing. We're trying to combine sine and cosine. That's not going to work. So we need to use a trig identity that involves the squares, hopefully to change this from sine into cosine. That's our goal, right? So let's do that. And we will remember that sine squared x equals 1 minus cosine squared x. Okay, so we're going to substitute this in right there. So that becomes 2, and then we have to put parentheses around it because this is a quantity. So we're going to have to distribute, equals 3 plus 3 cosine x. Good news, we just have cosine now. So we're going to do the same thing we did last time. We're going to clean this up and shove it all on the left and hope that we've got something factorable. And now, so I distributed. Now I'm going to swim these guys over. So minus 3 cosine x equals 0. Good, that's the way I want it. And now I will rearrange this. And you know, I think I'm going to multiply it all by minus 1. Because I don't want to, I don't want this to lead with a minus 2 cosine squared x. That's where I got the idea. All right, so this will become positive 2 cosine squared x. I'm going to go in order of them by descending variable. This is going to become a plus 3 cosine x. And let's see, 2 minus 3 would be minus 1, but I'm multiplying it by minus 1. Okay. Now it's all cleaned up. Now I'm ready to go out of cosine mode and just into plain x mode and figure out how to factor this using our advanced factoring rules. So 2x squared plus 3x plus 1 equals 0. Remember, I multiply a times c and I get 2. So it has to multiply to positive 2 and add to positive 3. John's making these really cute. 2x squared plus 2x plus x. Again, I always taught my students that you make the little arrows to show that you're splitting that into 2 parts. It's still the same equation. You haven't caused any drama. You just broke it apart based on this rule. It multiplies to a times c and it adds to the middle one. I'm going to write that out. I didn't last time. We want 2 factors. Find 2 factors that multiply to a times c and add to b. Okay? 2 times 1 equals 2 times 1. And then 2 plus 1 equals 3. All right. Oh, and then I have to copy the rest of it. And then we factor in pairs. And let's see, I can take a 2x out of there and I'm left with x plus 1. And this is how you do this. You say plus 1. I'm factoring a positive 1 out of there. And so then my final, I put this part and this part together in case you don't remember how I do that. Okay, I hit it with my algebra stick using the 0 product theorem, right? If 2 things multiply to 0, then one of them or the other of them has to be 0. So 2x plus 1 equals 0 or x plus 1 equals 0. And then I shake those out and I get x equals negative 1/2 or x equals -1. Okay, that's all done in my not trig function mode. Now I can bring those answers out. I'm working in cosine, so I don't have to deal with reciprocal functions this time. Oh, I forgot the x. Cosine of x or cosine of x equals -1. I don't have any positive numbers. Remember last time we had the 2 and it was too big, or was it a 3? I don't remember. It was a 3. These are both reasonable values for cosine. So I'm going to grab my little uni circle. Cosine of -1/2 is going to be over here on this side of the circle. So I have -1/2 at 120, and I have -1/2 at 240. So 120, 240, and then cosine of x at -1, 1, 0, there it is, -1 at 180. So for this one, we have 3 values that work, and that's our right answer. Okay? These two give us that cosine. That one gives us that cosine. They're all the answers. John likes to write them in successive order. He would have put the 180 in the middle. I kind of like to see it like this because it shows me that you got those 2 answers from that one and that from that. It doesn't matter to me. All right. 85.3 is very similar to what we just did. I want to show it to you. But I want to move on to our second topic because that's going to fry your brain and I want you to have brain power left. Woo! Oh my gosh, everything's falling. Okay. This one involves tangent squared and secant. So we use the same one we used in the first one. We substitute tangent squared equals secant squared -1. There it is. And then we solve it and we're fine. Okay? This is another one where if secant is -1/2, then that would make cosine -2. No, cosine is never going to be a -2. So this one is very similar to that one. It doesn't add anything new to our understanding, so I'm going to skip it. All right? Because I want to talk to you about clock problems. And that's our part B. Now, here's the thing about clock problems that have become even harder since the time John wrote this book. He means analog clocks, not digital clocks. He means clocks with hands, right? And just to give you a little refresher, clocks have a big hand and a little hand. The big hand counts minutes. And the little hand counts hours. I have very fond memories of staring at the clock in my classroom when I was a little kid, first, second, third grade. Do you know I skipped kindergarten? That's a story in and of itself. I won't tell you that right now. But I used to sit and study the clock and just, count the minutes till I could go home. All right. Now, just like any proper word problem in algebra, we're going to talk about rates and times. Rate times time in this world introduces spaces because all around this clock are little spaces, right? We know there are 12 big, I put those too far apart. We know there are 12 big spaces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But in between are enough so that there's actually 5 spaces for every one of those, right? So, the rate of the minute hand equals 1 space for every 1 minute. Right? Or another way to look at that is in the full hour, it goes 60 spaces in 60 minutes, right? It goes all the way around. But the rate of the hour hand is quite different. It does not go all the way around for every hour, right? If it's going from 1 o'clock to 2 o'clock, in the whole hour, it only goes 5 spaces. So it goes 5 spaces for every 60 minutes, or 1 space per 12 minutes. All right, so here's a nice thing about these problems. The rates will always be the same, right? Because clocks don't change their time. This is the one that we reduced, so make sure you keep track of this one. 1 space for every 1 minute, 1 space for every 12 minutes, okay? Now, with that in mind, let's go to the first example, 85.4. The hands of a clock point in the same direction. In how many minutes will they point in opposite directions? Okay. It helps to draw a picture. Right now, let's just say they're both pointing straight up to noon. Now, they're going to have to move a little bit because they're both going to start moving, right? But maybe it'll be something like this will be, oh, this should be the shorter one. And then that will be the longer one. Something like that, right? But the little hand, and I kind of hate that John calls it the little hand. I wish that he would call it the hour hand. That will move a certain number of spaces, but the minute hand, the big, or the minute hand, will have to move that same number of spaces plus 30 more, right? Because it has to get opposite. So this guy will move a little number from where they both were. He'll move a certain number, but then the big guy is going to have to move that many plus 30 more because they have to be apart from each other. 30 minutes is directly apart, right? So how do we account for all that? Well, I'm going to have to flip. I don't want to flip. Where's my little book? It's time for the little book to step in and get involved, right? Okay, so we need to write some equations that will allow us to explain this. The rate of the big hand equals 1. That's always true, right? 1 over 1. The rate of the little hand equals 1 over 12. Always true, right? 1 over 12. That is a deal breaker, right? The rate of the little hand times the time of the little hand is going to be a certain number of spaces, right? We said the little hour has to move S spaces, but the big one, the rate of the big hand times the time of the big hand has to equal S plus 30, right? We said that rate times time equals spaces. So there we have our rate times time. We want the little hand to move S spaces, and then we want the big hand to move that same number plus 30 more. This tells us the rates that they travel. Now we need one more equation because we have 5 variables. RB, TB, RL, TL, and S. So, one other cool thing that we can do that's super easy is just say, oh, the time of the little hand is the same as the time of the big hand, right? They're both moving together. So, this one, and this one are like true of every situation. The only thing we really had to come up with that's unique to this problem is this. That's good news because once you understand those 3 equations, you're 3/5 of the way to getting every problem set up. All right? Now, how are we going to solve this? John suggests we begin by substituting into the first 2 equations just a second. I'm trying to figure out what he is doing. Oh, okay. We know mine are kind of mixed up, but if we put this rate into this equation, and this rate into this equation, it'll look nicer, right? So we'll get, if we put this in here, then we'll multiply 1/12. Here, let me just do it. Okay, so if we multiply 1/12 in here against TL equals S, we can rewrite that just so it looks cuter. We can put TL on the top over 12 equals S. There's a new equation, right? We just substituted that in there. Now, when we do the same thing over here, we'll do 1 times TB equals S plus 30. And that we don't even need, so we can just say TB equals S plus 30. Another much better equation. Now, because these both have an S in them, we can rearrange. Well, just watch. I'm ready to switch my page, though, now. Okay, so we've got TL over 12 equals S, right? That's what I have right here. And now I'm going to copy this one down. I'm going to put it over here. TB equals S minus 30. Now, just playing algebra games, I'm going to add 30 to the other side. So TB plus 30 equals S, right? I just rearranged it. Now, look at these two. They're both equal to S. So now I can bring them together and say TL over 12 equals TB plus 30. Except I made a mistake. Oh no. It was just in my copy. This was plus 30 all along, right? Because it has to move the same number of spaces as this guy, plus 30. When I copied it over here, I just copied it as a negative. So that's plus, and so this is the negative. Okay? That was just a copying mistake as I went from page to page. Actually, it was kind of hard to see right there. All right, so we're back on track. This should be a minus 30. All right. Now, here's good news. We also said that the two times are equal to each other, right? The time of the little equals the time of the big. So we can just take the subscripts off and we can just rewrite this as T over 12 equals T minus 30. And now all we have to do is cross multiply and solve. So I'll cross multiply and I'll get 12 times the quantity, T minus 30, equals T. 12T minus, wow, 360, right? Equals T. Now I'm going to subtract T from both sides, and I'm going to add 360. 11T equals 360. And what that means is that the amount of time that needs to elapse before those hands are opposite is 360/11th minutes. That's correct, but how unsatisfying is that? It turns out that it's 32 and 8/11ths if you want to put it in a mixed number, which I don't expect you to do that, but it just helps. It's a little more satisfying to know, right? This doesn't really feel very satisfying. Woo! All right, that was a lot, right? The hardest part, though, is setting up these 5 equations. And like I said, 3 of them are going to carry forward to all of these problems, right? Because they just describe how a clock operates. So we will do the second and final example for this lesson, and then hopefully it will feel a little bit better for you. Example 85.5. Before we even start, I'm going to write down the 3 things that I know. The rate of the big hand is always equal to 1. The rate of the little hand is always equal to 1 over 12. And the time of the little hand always equals the time of the big hand. Fabulous. Now I'm going to write down 2 more. It is 3 o'clock. Big hand straight up, little hands there. I exaggerate them. Wouldn't that be a funny clock? In how many minutes will the 2 hands of the clock point in the same direction? Okay, well, it's going to be kind of like this, probably, right? It'll be a little bit like 3:17 or something like that, right? Because this one will come down here, and then this one will have gone a little bit. Okay, so we always start by saying that the rate of the little hand times the time of the little hand equals a certain number of spaces, and then the rate of the big one times the time of the big one equals spaces plus 15 in this case, right? Because we need it to be pointing in the same direction. So it's got to catch up these 15 minutes, right? 15 minutes per quadrant on a clock. So it's got to catch up the 15 plus move the same number of spaces as that guy. All right, so there we have our 5 equations. 1, 2, 3, 4, 5. And now we just do the very same thing that we did last time. We put the rates in here. I'm going to do it in one step this time. The rate goes in there. I'll drop the subscript on the time. The rate goes in here. I'll drop the subscript on the time. Then I'll subtract the 15. I'll do that in the next step. Let me do this much first, right? Okay, so this is 1/12, but the t goes in the top, equals s. And then the bottom one, the rate, that's 1. So t equals s plus 15. So now I'll swim the 15. Then they'll both be equal to s. And I'll write that. T over 12 equals t minus 15. Right? The s's connected. I swam that over. And now I'm ready to solve. T equals 12t minus, let's see, what's 12 times 15? I don't want to guess. $170. Okay. I'll swim the t this way, and I'll add 170 to both sides. 170 equals 11t. Notice how we keep getting this 11t because it represents the difference between the 12th and the 1. That's where the 11 comes out. It goes through our algebra, but that is how come these will very often end with a denominator of 11. Oh, yeah, I'm fine. No, this is 180. Did I? Oh, yeah, I added wrong. See, I knew my brain was just a bit much. Okay. That was just my bad. I even multiplied right. I just didn't add right. That was sad. I was thinking of this 5 and 2. Okay, and then we just divide by 11 to finish this off. And we get t equals 180 over 11. And then minutes, if you want to put the word on there. And again, this is a perfectly fine answer, but I'm always sort of curious. It's 16 and 4/11 minutes, which is just what we thought, right? The amount of time that it would take. This guy would just take a couple minutes. Turns out it's just 1 4/11 of a minute for him to come cruising down. Okay. Clock problems. Very sophisticated and advanced. The math isn't terrible. It's kind of fun, really, right? But just wrapping your head around how those hands move, and even in this world, if you guys don't have analog clocks in your life, this kind of clocks, get some. Even you can just switch your phone over to an analog clock, right? But make sure you have a few in your life while you're working on these problems, just so that you remember how they work, because we have so many digital clocks now. It's harder to visualize some of this. Okay, I hope your brains are healthy. Goodbye.